Hello and welcome to lesson number 14, limits. Before we talk about limits, we must first talk about functions. A function is an operator that takes an input and turns it into some output. Basically, you put some x into here and it changes it and gives you some other output. For our purposes, we are only going to be considering functions that take real valued inputs and produce real valued outputs. The reason for this is because within our syllabus, we don't like to touch complex numbers within limits. Of course, however, you can do limits with complex value outputting functions or even complex value inputting functions. But for our purposes, we will be ignoring that and only considering functions that take some value along the real number line and produce it into some other output which is also along the real number line. An example of such a function is f(x) is equal to 2x plus 1. This function takes some input x along the real numbers and produces some output 2x plus 1 or fx along the real numbers. Let's say I want to find f of 1. What does this mean? This means I want to find the value of fx when x is equal to 1. In this case, it's quite easy to do. I just substitute the value into here and do 2 times 1 plus 1, which is 2 plus 1, which is 3. So therefore, f of 1 is equal to 3. In this case, it's not a problem. We can easily find the exact value of f of 1 simply by doing a substitution. Sometimes, however, it becomes more difficult to find the value or perhaps impossible to find the value using this method. An example of such is this. Consider the function fx is equal to 1 divided by x squared. Can we find the value of this function at x equals 0? Well, first off, let's see if we can find the value of this function at some other x. Let's say f of 2. F of 2 is 1 divided by 2 squared, which is 1 divided by 4, which is 0.25. I'm going to leave it as 1 divided by 4 and say that this is the answer. How about f of 0? Well, f of 0 would be 1 divided by 0 squared, which is 1 divided by 0, which is undefined. So, is that it? Is that where we end? F of 0 is undefined. It's 1 divided by 0. Well, that is how we end for substitution. We cannot substitute f of 0 as in, we cannot substitute x equals 0 into fx and then get a proper answer. In this case, it is undefined. However, limits allow us to actually find this value as an exact value. It's not nice value, of course, but we can find where f of 0 seems to be going, not exactly where f of 0 is, but rather where f of 0 seems to be going. So, the idea of a limit. A limit is basically asking, instead of what the value of a function is, what does the value of the function look like it's going to do as you get really close to the value that you're interested in. For example, the limit as x goes to 1 of 2x plus 1. What this right here is an operation. We are asking lim, as in the limit of 2x plus 1 as we make x very close to 1. So, what happens when you make x very close to 1? Well, the graph of this function looks something like this, which will help us actually. Over here, the graph looks like this. Over here, this value is 1, this is 0. At 0, this is 1. At 1, the value is 3. And if we mark 2 as well, at 2 the value is 5. So, what we want to do here, what we want to do with this operator is look at x's that are getting closer to 1 and see what 2x plus 1 seems to be getting closer to. Now in this case we do have the exact value, it is 3, but let's just look at where it seems to be going. So, to get closer to 1, there are multiple ways you could do it. You would get close to 1 from the right hand side or the left hand side. X could get close to 1 like this or like this. In fact, when considering a limit, we need to consider both of these cases. Each of these cases have their own special notation. This case, going from a larger value of x down to the value of x you intend, is called right-handed limit or the positive sided limit. It's written like this. LIM, again same notation, x approaching the value you're interested in this case 1, but then you add a little plus here to indicate that you want to get close to 1 from the plus direction or the positive x direction. You get close to 1 from some value which is to the right side of the positive x direction to your intended value. So this first operation, which I'm actually going to color these in two separate colors, we'll erase these two arrows here and put them in two separate colors. Let's say the right side limit we represent in this red, and the left side limit we represent in this light blue or cyan. So here, this is the red limit. The limit as x approaches 0 from the plus direction is the red limit. So then that limit of 2x plus 1 is one value. Similarly, if we go from the other side, the blue limit, the limit as we go from the left hand side, as we get close to x equals 1, from the left hand side would be written as lim x little arrow 1 from the negative side, written with a small negative here, of 2x plus 1. So the way this is defined, this limit here has a certain value. This value is a valid limit given that both of these two, the red limit and the blue limit, give the same value and agree with each other. And the value is for a proper limit it has to be finite, but for our purposes for now we are just going to consider whatever the value it is, it should be the same value on both sides. So in this case, for the red limit, what this means is that we want to get x's that are greater than 1 but not equal to 1, and we want to make these x's really close to 1 and see what happens. So let's try 2. For 2, if we substitute 2 into here, we get 2 times 2 plus 1, which is 5. If we instead try a number that is closer to 1 but still greater than 1, let's say 1.5, 1.5 substituted into here will be 2 times 1.5, which is 3, plus 1, which is 4. If we try a value that is even closer, let's say 1.1, we will have 2 times 1.1 plus 1, which is 2.2 plus 1, which is 3.2, which is close to 3. In fact, as we try and keep getting closer and closer values to 1 from the positive direction, like this, we will be getting an output which is going to get closer and closer to 3. So therefore, on the right hand side, the limit as x approaches plus 1 from the positive direction is going to be equal to 3. So I'm going to write that here, this is equal to 3. How about from the minus side? Well, in this case, we want to choose a number that is less than 1 but getting closer to 1. If we do a half here first, substituting a half into here, we have 2 times a half plus 1, which is 1 plus 1, which is 2. If we instead try a bigger value, let's say 0.75, which is about here, this will give us a value that is closer to 3. So here, if I represent closer and closer values to 1 like this, our output will be getting closer and closer to 3. In fact, as we approach the limit, as x approaches 1 from the negative side, we do in fact get the value 3. So the limit as x approaches 1 from the negative side is also equal to 3. So therefore, the right side limit and the left side limit agree. The red limit, meaning the right side limit, meaning the positive limit, is equal to 3. The left side limit or the negative limit is also equal to 3. Since both of these limits are getting closer to 3 as we get close to 3, we say that the limit from both sides, or simply just stated the limit as x approaches 0, x approaches 1 of 2x plus 1 is equal to 3. Now, you might be wondering why in the hell we want to do this, why we want to consider the red side and the blue side separately and then bring them closer. It's because sometimes it doesn't work out. Sometimes the red limit will give us one value and the blue limit will give us another value which do not agree, in which case we cannot write that the overall limit is any particular value. An example for this, which I will write next, is the function, let's say gx is equal to 1 divided by x. Let's consider what g0 is. G0 would be 1 divided by 0, which is undefined. So, how do we find it? Well, if we draw the graph of gx looks like this. If we plot the graph, here we have the x-axis, here we have the y-axis. Let's just test some values. Here we have 0, which we obviously cannot test, but we can test other values. If we test x equal to 1, 1 will give us 1, because 1 divided by 1 is equal to 1. So therefore the output here is going to be 1. X equal to 2 will give us a half, which is somewhere here. So here, this is the value corresponding to x equals 2. X equals half over here will be 1 divided by half, and 1 divided by half is 2. So the value corresponding to this will be somewhere up here like this. The next value after that we can do maybe a fourth, and a fourth will be 4 because 1 divided by 1/4 is a 4. So that will be somewhere up here. We can see here, if we connect these dots, the graph of 1 divided by x seems to be getting higher and higher. If I draw a smooth curve, if I somehow manage to draw a smooth curve, it will look like that. We can see for bigger and bigger values, the smaller and smaller values of x from the positive side, we are getting closer and closer to a very large value of y, as in y equals infinity. So if I draw the red limit here, as we get values that are closer and closer to 0 of x from the right hand side, our value is getting closer and closer to infinity. I'm going to now erase these guidelines in the middle. These guidelines are actually unimportant. We only really want the curve itself. So here, as we can see from the curve, as we get bigger and smaller values of x, we get bigger and bigger values of y. So here on the right hand side, it seems that we are going to be approaching positive infinity as we get x's that are closer and closer to 0 but to the right side. However, on the left side, if we look at the left side, on the left side, let's say we consider -1. 1 divided by -1 is -1. So over here, the corresponding value is -1. If we consider -2, 1 divided by -2 is a -half. So we have -half over here. How about -half? Well, x equals -half will correspond to 1 divided by -half, which is -2. If we do -1/4, we get -4. So you can see on this side, if we connect these dots and draw the graph looks like this. If I draw it somewhat nicely with a smooth curve, it'll look like that. There we go. So erasing the guidelines here, erasing all of these guidelines and leaving only the graph itself behind, the graph looks like this. As we get closer and closer to 0 from the left hand side, it appears that our values are getting closer and closer to -infinity. We can see we're getting bigger and bigger negative values. So now, if we consider the red limit and the blue limit, I'm going to draw them again as the red limit and the blue limit like this. Considering the red limit is written as the limit, as in this case we're interested in 0, so x approaches 0, and we're going from the positive direction or the plus x direction, so therefore there's a small plus here. This is the limit as x approaches 0 from the plus direction of gx. And as we can see from the graph, when we get smaller and smaller values of x that are in the positive direction, our output is getting closer and closer to positive infinity. So therefore, the limit as x approaches 0 from the positive direction of gx is in fact positive infinity, which I'm going to write as a plus infinity. How about the blue limit? Well, the blue limit is written as the limit as x approaches 0, but we are interested in going from the negative direction, so therefore we are going to have a negative sign here. We are interested in the function gx, and if we look at the graph, we can see as we get values that are closer and closer to 0 from the left hand side, we can get bigger and bigger negative values. So therefore the limit as x approaches 0 from the negative direction of gx is going to be -infinity. Now, we can see a discrepancy here. The red limit says that when we get close to 0 from the positive direction, we get positive infinity as our output. The blue limit says that as we get closer and closer to 0 from the negative direction, we get negative infinity. So, which is it? What is the limit as x approaches 0 in general of gx? Well, this limit does not exist. It does not exist because the red limit and the blue limit, the limit from the right hand side and left hand side, do not agree with each other. So we can say as a condition we could say the limit as x approaches a of, let's say, fx exists if and only if, we need this thing to exist if both the red limit, which is the limit as x approaches a from the positive direction of fx, is equal to the limit as x approaches a from the negative direction of fx. Both of these limits, as we go from the right hand side and left hand side, need to be touching at the same exact value in order for them to agree, and thus for us to say in general the limit as x approaches a for any a in the real numbers exists. So here we can write as a condition for a element of the real numbers. So in this case we have our first theorem. I'm going to put a star here and write this as a theorem. The limit exists, which is now we're defining it. The limit as x approaches a exists if when we go from the right hand side and the left hand side we seem to be going towards the same value. So here as a general theory, if the limit goes to the same point from the left hand side and right hand side, then the value exists. So here I'm going to put this equal to some value which I'll call L. If both of these limits are equal and they approach the same value which I'm going to call L, then we can say that the overall general limit exists. If not, then the limit from the right hand side or lim x goes to 0 in the plus direction is one value, and the limit x goes to 0 from the minus direction is another value, then the limit as x approaches 0 in general does not exist. Because from the right side it's one value, from the left side is another value. Over here, above here, we could say that the limit x approaches 1 of 2x plus 1 is equal to 3 because the red limit or the right hand side limit and the blue limit or the left hand side limit both agreed on the same value, x equals 2x plus 1 equal to 3. So let's now review a case where we seem to have something undefined at the actual point. Now in this case g of 0 was undefined and the limit was also undefined because it does not exist, it does not agree. The blue limit and the red limit do not agree. Let's now look at another function in which even though the actual value does not exist, is undefined, the limit can be agreed from both sides. Let's say hx equal to 1 divided by x squared. And again of course we're going to consider h of 0. H of 0 is 1 divided by 0 squared, which is 1 divided by 0, which is undefined. However, if we draw this graph, let's draw it real quick and observe the shape of this graph, we can see something like this. Let's draw x here and y here. So again 0 we cannot substitute because h0 is undefined. But if we do 1, let's do 1. H of 1 is 1 divided by 1 squared, which is going to be 1. So here 1. We have a matching point. For x equals 2, what we have h of 2 is 1 divided by 2 squared or 1 divided by 4. So something like this. This is going to be h of 2. H of a half. H of a half is 1 divided by half squared, which is 1 divided by 1/4, which is 4. So this is going to be 4. So up here, all the way up, somewhere like that. If I connect all of these dots, we can see the graph is going to be something like this. It's not exactly the shape, but of course the shape is irrelevant to us, just what it looks like. So here, the graph of 1 divided by x squared or h of x is going to look something like this on the right hand side. How about the left hand side? Well, if we try -1 here, -1 here, h of -1 is 1 divided by -1 squared, which is 1 divided by -1 squared is going to be equal to 1. So it's 1 divided by 1, which is 1. So h of -1 is equal to 1. In which case the output correspondent is this point, which I'm going to mark right here. Similarly, for -2 is going to be -1 divided by -2 squared, and then 1 divided by -2 squared is going to be was 1 divided by 4, which is going to be 1/4. So here this is the corresponding point as 1/4. Similarly at half, -half squared is going to be 1/4, then 1 divided by 1/4 is going to be 4. So the value corresponding to that is going to be here. If we draw the graph, it's going to look like this. So now here we can see from the left hand side, if we consider the blue limit, and the right hand side if we consider the red limit, I'm going to draw those out. The blue limit as x approaches 0 and the red limit as x approaches 0 are both going towards a positive infinity. We can see here this is going up and this is going up. If I write those limits separately, I'm actually going to move this whole thing to the left a bit and give us a little space over here. If we write out the red limit and the blue limit as red limit and blue limit, the red limit is written as limit as x goes to 0 from the positive direction of h of x. This is equal to, as we can see, when we get smaller and smaller x's, we are going towards positive infinity. So therefore this is equal to positive infinity. The other limit as x goes to 0, but from the other direction, the negative direction, so we rewrite x goes to 0 from the minus direction of hx, is equal to still positive infinity. From this side as well, we can see as we get closer and closer to 0, but we go from the negative direction, we are going towards positive infinity. In this case, even though h of 0 is undefined, we can see that the red limit and the blue limit are in agreement. If the red limit and the blue limit are agreement, then the general limit is also defined. So the limit as x goes to 0 in general of hx is going to be positive infinity. So here we can see our first rule saying that if the red limit and the blue limit are both agreeing on the same value, then the final limit is also going to be equal to that value. But now there's a little caveat. This is how we define it. If a limit is infinite, we say that it's not a proper limit. For a proper limit, we want a proper limit to be finite. So we're going to write that as a rule down here. A proper limit is finite. A proper limit is finite. So over here we're going to introduce a few more bits of terminology known as convergence and divergence. Convergence and divergence to help explain what we mean by finite limits, infinite limits, and limits agreeing. Within limits, we say that if the limit is a finite value and both sides agree, then it is a convergent limit. So here, if we have a convergent limit, convergence means the limit as, let's say, in general x approaches a of fx is a finite value. And of course, we also need the case that the blue limit and the red limit agree. So that would anyway not be the case if the two do not agree. So first off, the limit as x approaches a of fx needs to exist. If it exists and both sides agree, then given that it's a finite value, we will say that it's convergent. If not, if anything else, i.e. anything else like red and blue don't agree, or infinite. In fact, I'll write these down, infinite, and then we could also say red limit, blue limit. These are not called the red limit and blue limit in general, by the way. It's not what everyone uses. I'm just using this terminology because that's how I introduced it. If the red limit and blue limit do not agree, or the limit is infinite, or we have some other issue, like we'll just say for now other issue. If we have some other issue and we cannot find the exact value, then we say that the limit is divergent. If the limit is agreeing from both sides and the limit is a finite value, only then do we say the limit is convergent. So if someone tells you that the limit as x approaches a of fx is convergent, what they mean is that from the right side and from the left side, the red limit and the blue limit, or the positive side limit and the negative side limit, agree on the correct value, and the value is a finite value. In that case, the limit is convergent. So now let's look at some rules of limits. One simple rule of a limit is that if we have the limit as x approaches a of a constant k, this is simply equal to k. This shouldn't be too hard to understand. In this case, what we are asking is what happens as x gets really close to a to the value of k. But k is a constant, so nothing happens. It's still k. In fact, if we draw the graph, we can see this quite clearly. Let's just draw the graph of this thing. If we have a constant k, then on a graph, the value of k will look something like this. Let's say k is a positive number, in which case k will look like this. This is k. For any real value x, y is simply equal to k. So no matter what a is, approaching a from the left or right doesn't matter, the value is still going to be k. So therefore, the limit as x approaches anything of a constant is equal to that constant. We can use this easy to simplify certain functions where we have a constant on the inside of a limit. We just take it out and say it's equal to the constant. A similar another rule is that if we have the limit as x approaches a of a constant times a function, let's say a constant k times f of x, we can take the constant out of the limit and say this is k times the limit as x approaches a of f of x. Again, we can simply take this out. Again, if you really want the logic of this, it's because here we just have a multiplication of a certain value. Multiplying by a constant does nothing to the actual limit, provided of course that k is not 0. If k is not 0, still we'll get a correct answer, but it's kind of nonsensical. So we'll forget that for now. If we have a constant times a function and we are taking the limit of that, the limit operator of this thing, it's the same as multiplying k by the limit operator of fx. Another useful thing is that if we have the limit as x approaches a of the sum of two functions, let's say f of x, we'll say plus or minus g of x. If we are adding two functions together, the limit operator of that sum is equal to the limit operator as x approaches a of the first function plus minus the limit operator as x approaches a of the second function. So here we can see if we have a sum of two functions and we take the limit of it, then it is the same as taking the limit of each individual function and taking the sum of that. We write this and say this in a common, kind of, I suppose, mnemonic way to try to remember it, saying that the limit of a sum is the sum of the limit. You could write that down if you want. The limit of a sum is the sum of the limits. This is like a common thing that most people say to remember this simple rule. If you have the limit of a sum of functions is the same as the sum of each of the limits of the functions. Of course, there's certain issues here, like each of these functions need to exist and be proper limits, of course, because otherwise then you would have something undefined in the middle here. This would also be undefined. But let's ignore that and just say that the limit of a sum is the sum of the limits. A similar rule to this is that the limit of a product is the product of a limit. If we have x approaches a of f of x multiplied by g of x, as in a product of two functions, this is the same as the limit operator of the first function multiplied by the limit operator of the second function. Again, for this thing we need all of these limits to be proper limits and valid, because otherwise we would have potentially some limits that are valid but some limits that are invalid. So all of these need to have the red limit and the blue limit being equal, agreeing to each other, being a finite value, all of that. Given all of that, then the limit of a product is the product of a limits. As another one, similar to this one, of course, the limit as x approaches a of fx divided by gx is equal to the limit as x approaches a of fx divided by the limit as x approaches a of gx. Now here there's another condition. Of course, whenever you divide, you need to always have the condition that what you're dividing by is not equal to 0. So this thing is only valid for limit as x approaches a of gx not equal to 0, because otherwise we have a divide by 0 in our case, which is a little issue. So excluding that case, any other case, the limit as x approaches a of gx not equal to 0, then limit as x approaches a of fx divided by gx is the limit of the first function divided by the limit of the second function. Similarly, there's another two, the limit as x approaches a of a function to the power of n is equal to the limit as x approaches a of the function whole thing to the power of n. So the power of a limit is the limit of a power. But here, because of various reasons like complex numbers and divide by 0 problems, we have to restrict n to be natural numbers within our syllabus, because we don't want to talk about stuff that's not natural numbers. So n is limited to within the natural numbers for this thing. Similarly, the limit as x approaches a of the nth root of fx is equal to the nth root of the limit as x approaches a of fx. Once again, due to various issues like divide by zeros and taking the square root of negative numbers, we need to impose restrictions saying that again n needs to be a natural number, and another restriction saying that fx greater than or equal to 0 for the valid range. So here what we mean by this is that we don't want to be taking any square roots of negative numbers within the ranges we're considering for the limit. Other than that, we are alright. So that's that. These are the bunch of rules that are there within our syllabus regarding limits. There's a couple more that are outside of our syllabus, but these are within our syllabus. Now that we've discussed some certain properties of limits, let's discuss some theorems on limits that we can use and are expected to use within papers and other applications within our day-to-day life. In terms of theorems on limits, we don't have all that many, there's just a few. One important theorem on limits is that if fx is a polynomial, then the limit as x approaches a of fx is simply equal to fa, meaning that we can just substitute the value that we want into the function to get its value at a certain limit. This becomes useful, and this is true because of course fx as a polynomial is a well-behaved function. It is never going to be undefined for certain values. We'll never have a divide by 0 within a polynomial as fx. So because of that, we can just simply say the limit as x approaches a for any a of fx is simply equal to f of a. This becomes useful in simplification where you have certain limits with polynomial parts and non-polynomial parts. The polynomial parts can easily be substituted with their exact values. Another useful theorem is something called the squeeze theorem, sometimes called the sandwich theorem. So this idea of the squeeze theorem is a little bit more complex, and we need to get a little bit more into it if we want to explain it. So basically, if for a certain interval containing a. What I mean by a certain interval containing a is a range of inputs of x. Let's say on the infinite number line, there's a certain value a somewhere here, and the range of inputs from a certain value to certain value such that a is somewhere in the middle of them is what we mean by an interval containing a. If for a certain interval containing a, we have the condition that some function, let's call it a gx, is less than or equal to fx, which is itself less than or equal to hx, meaning that fx is somewhere in between gx and hx for all the x's within this interval that is also containing a, and we also have the condition that g of a is equal to h of a is equal to some limit, let's say L, some value L. In this case, we can say then, this is the actual part of the theorem, then the limit as x approaches a of f of x is also equal to that same value L. The intuition behind this thing is to simply imagine what these functions look like on a graph and then understand that this has to be the case. So if we draw this out on a graph, we can clearly see why the limit as x approaches a of fx is also equal to L. So drawing this out on a graph, I'll just draw a random graph like this. And let's say the red line, for example, is fx. This is fx. Let's say that this orange line is the function gx, which is less than fx. So gx is less than or equal to fx for all the values. Let's say we mark the special value over here, a. So here we have gx, and gx, let's say it looks something like this. So here we can see gx over here is always less than or equal to fx. Let's take the other function which we have over here, which is hx. The function hx, which is greater than or equal to fx, we'll call it by purple. So then drawing that on the graph, hx would look something like this. So let's just say hx looks something like that. here we can see hx, the purple function, is always greater than or equal to the red function fx. So here if I mark these down, this is hx, the red one is fx, and the orange one is gx, and we can see h of a is equal to g of a, which is this same value L. So over here, this height here is what I'm going to be calling L. We can see here h of x is equal to L, and similarly h of a is equal to L, and similarly g of a is equal to L. Given this, and given that f of x is somewhere in between h of x and g of x for some valid range, then we can say that, and we can see that f of a should clearly also be equal to this value L. So here this is just a visual interpretation of it to help you understand. We can go into more rigorous methods of showing this, but for now this is going to be sufficient for us. It's just a simple demonstration that if for a given interval f of x is between h of x and g of x, and that interval contains a value a such that h of a is equal to g of a, that is, on the left hand side this is equal to L and this is equal to some value L, then the value in the middle should also be crushed in between these two functions and should approach the same limit L. You can see that since f of x is between these two functions, as the two functions converge onto this point here, f of x is kind of crushed, it's squeezed between the other two functions, hence the name, the squeeze theorem. This theorem is useful when you have a function that you're not really sure about, but you have two other functions that you are sure about and that you're sure are bounding this function. So we can see here, this is a bound, this is a bound. We have the less than or equal sign here and here. So therefore, these two functions are bounding of the central function fx, at least within the interval containing a. And then given this condition, we can define define a value L, and that value L is equal to this g of a and h of a, meaning that since f of x is stuck between g of x and h of x, the limit as x approaches a of f of x must also be equal to L. So now that we've covered that, let's go on to some common results in limits. One common result in limits is that the limit as x approaches a of x to the power of n minus a to the power of n divided by x minus a is equal to n times a to the n minus 1. So let's prove this thing right here. One way to prove this is to simply try and divide this thing on the inside. You'll notice if we try to substitute directly, if we try to substitute x equal to a into here, we have a to the power of n minus a to the power of n divided by a minus a, and a to the power of n divided by minus a to the power of n is equal to 0, divided by a minus a is equal to 0. We have 0 divided by 0, which is undefined. So we cannot do it by the old-fashioned way of substituting. We must do it by limits. So alright, that's out of the question. Next thing we can do is try to divide this polynomial inside. So to do this, we have to consider x to the power of n minus a to the power of n divided by x minus a. Recall in polynomial division, what we want to try to do is eliminate the highest power term with our denominator here. So what do we have to multiply x minus a by in order to get an x to the power of n? Well, we need to multiply it by an x to the power of n minus 1. X to the power of n minus 1 times x minus a will give us an x to the power of n, because here we have x to the power of n minus 1 and another x to the 1. Multiplied together, that will give us an x to the n. We additionally have an negative a times x to the power of n minus 1. So we have minus a x to the power of n minus 1. If we do this division, we'll see what we are left with. So writing this in long division form, the first thing we have to do is x to the power of n minus a to the power of n and x minus a. We have to divide first, and then when we divide, the first thing we have to take out is an x to the n minus 1. Doing that, we got an x to the n, and multiplying these two, we additionally got a minus a to the a x to the n minus 1. Now subtracting these two, what we are left with, well, this thing cancels out, this x to the n and this x to the n cancelled out. Subtracting a minus a x to the power of n minus 1 will give us a x to the power of n minus 1 and then a minus a to the power of n. Next, we need to try to get rid of this. To get rid of this, we first need to get rid of the highest order term, which is ax to the n minus 1. To get rid of ax to the n minus 1 with an x minus a, we need to multiply x minus a by a times x to the n minus 2. So we have to have a times x to the n minus 2 here. So then, alright, we have that. We have to then multiply that by x minus a and get rid of whatever that's left over here. So, ax to the n minus 2 times x minus a will give you ax to the n minus 1 minus a times a, which is a squared, times x to the n minus 2. If you cannot see that, just multiply this thing by this thing and subtract it. A x to the n minus 2 times x to the 1 is a x to the n minus 2 times x to the 1, which is a x to the n minus 1. And minus a times a x to the n minus 2 is minus a squared times x to the n minus 2, which is this. Now subtracting that off, what we are left with, these two cancel. We have just a squared x to the n minus 2 over here, and then minus an a to the power of n. We can keep repeating this. I'll do one more until you see the pattern, and then we'll continue it. So the next thing we have to take out here is going to be an a squared x to the n minus 2. To get rid of that, what we need here at the top is an a squared x to the n minus 3. Multiplying that by x minus a will get us 1 a squared x to the n minus 2, x to the n minus 2, but it will also get us a minus a times a squared x to the n minus 3, which is minus a cubed x to the n minus 3. Cutting that out, what we have next is an a cubed x to the n minus 3 minus an a to the power of n. If we continue this pattern down, what we will end up with is a sum of all of these terms like this. If I write out that sum, you can see the pattern here. If I at the start put an a to the 0, you can very clearly see it. This is a to the 0, this is the a to the 1. What we have is an a to the 0, a to the 1, a to the 2 continuously, and x to the n minus 1, x to the n minus 2, x to the n minus 3. So the very last term is going to be, the term before the last term is going to be a to the n minus 2, x to the power of 1, and the term after that is going to be a to the power of n minus 1, x to the 0, or just a constant term. So if I replace the entire sum like that, if I cut this out, this division, and replace the entire sum with that, what this is going to be is the limit as x approaches a of the sum of x to the n minus 1 plus a times x to the n minus 2 plus a squared times x to the n minus 3 plus ... all the way down until a to the n minus 2 x to the 1 plus a to the n minus 1. We have this. So now, what's this equal to? Well, over here we have a sum of terms, and the sum of the limit is the limit of the sums. So we can take the sum limit of the sums, break it into the sum of the limits, and say this is equal to the limit as x approaches a of x to the power of n minus 1 plus the limit as x approaches a of a times x to the power of n minus 2 plus ... all the way down to the limit of x approaches a of a to the n minus 2 x to the 1 plus the limit as x approaches a of a to the n minus 1. So here, over here, we can substitute a into this one. Right here, we can substitute a directly because this right here is a polynomial. Substituting a directly into here, we have a to the n minus 1 plus. The next thing is also a polynomial. We have some power of x. Substituting a into here, we can get a times a to the n minus 2, put a dot here for the times, plus the next term after that would be a squared times a to the n minus 3 plus ... The last term here is a to the n minus 2 times x to the power of 1, so that will be just a to the power of 1 or just a. And then the very last term will be a to the power of n minus 1. So if we look at all of these, we can see the first term is a to the power of n minus 1. The second term is a to the power of 1 times a to the power of n minus 2, which is just a to the power of n minus 1. The next term after that is a to the power of 2 times a to the power of n minus 3, which is just a to the power of n minus 3 plus 2, which is a to the power of n minus 1, and so on, all the way down to here where we finally have a to the power of n minus 2 plus a to the plus 1, which is going to be a to the power of n minus 1 and a to the power of n minus 1. So we have a certain number of n minus 1s. How many n minus 1s do we have here? Well, if we start looking, we can see we have exactly n number of n minus 1s. So altogether we have n number of n minus 1s. Therefore the sum here is n times a to the power of n minus 1. How do we know there's n number of n minus 1s? Well, look at this sum here and you can see it clearly. Here the final term is x to the power of 0. If we start counting, we have 0, 1, 2, 3, 4, 5, 6, 7 all the way up to n minus 1. Counting from 0 up to n minus 1 is the same as counting up from 1 to n. From 1 to n there are n number of terms, so therefore there are n number of a to the n minus 1s here. Therefore our sum total is n times a to the power of n minus 1. Therefore the limit as x approaches a of x to the power of n minus a to the power of n divided by x minus a is n a to the n minus 1. Therefore we have proven that the limit as x approaches a of x to the power of n minus a to the power of n divided by x minus a is equal to n a to the n minus 1, hence proven. So there's one more important resource that we have, one more important limit that we must remember and must use. It's there a lot in papers and you will see it, and that is the limit of the limit as x goes to 0 of sine x divided by x. Over here x is going to be in radians. So let's go ahead and prove this thing. This is actually equal to 1. However, if you try to substitute directly, you can see substituting x equals 0, we have sine 0 divided by 0. Sine 0 itself is 0, so here again, once again we have the same issue of a 0 divided by 0. So therefore substitution is not going to work here. We in fact need the help of limits in order to solve this one. And actually to solve this particular problem, we are going to be using the sandwich theorem. So here I have drawn a construction which we are going to be using in order to find that the limit as x approaches 0 of sine x divided by x is equal to 1. Here I have a unit circle. This length OA is equal to 1. So therefore this circle is of radius 1. It's a unit circle. And I've drawn the line AC such that it's tangent to the circle. So therefore this length is going to be tan of theta, the tangent of theta. And then within the circle I've drawn a point D such that OA is perpendicular to AD, and therefore this length here AD is sine of theta. So now within this construction that I've drawn here, I want you to consider certain areas. I want you to consider first the area OAB, which I'm going to now color in with red. And then I want you to consider this extra little area here within this curved part, and then I want you to consider this external area here outside of it, which I've drawn in purple. So if you consider the areas of the triangles OAD, OAC and the area of the sector OAB, we can see some certain things. We can see that if I write this out, the area of triangle of, I'll put off here as well, the area of the triangle OAB is less than, we can clearly see it's less than the area of the triangle, actually it's also less than the area of the sector OAB, and it's also less than the area of the triangle OAC. We can clearly see that because between the triangle OAB, which is the red area, there's an extra bit of area, the green area, which is also there in the sector, this curved part of the circle here, OAB. So therefore the area of OAB sector must be greater than the area of the triangle OAB. And then similarly, since the other triangle OAC is bigger than this sector, meaning it has some extra purple area which is not there in the sector, its area must also be bigger than the sector. I am going to include some equal signs here because in fact when we make this angle really small, which we don't know yet, we cannot see it yet, but when we make this angle really small, each of these areas will converge onto the same exact area. But for now I'm going to just leave it as with a equal sign, meaning that we can have all three areas being equal to each other. So now let's try to write each of these areas down in terms of some trigonometric functions. It's easy to write the largest area, the area OAC, out because we can see here at a OAC angle is 90 degrees. This is a base and this is the height of the triangle OAC. As we know, the area of a triangle is half into base into height, so therefore half into base into height here is half into 1 into tan theta. So that's half into tan theta. So the area of OAC triangle is half into 1 into tan theta, so I'm going to write as half tan theta. And then the other two areas, well, the area of the sector OAB here is the fraction of the circle that this angle takes up times the area of the total circle. The area of the total circle is pi r squared, and the fraction that this thing takes up, this theta, provided that theta is in radians, is going to be theta divided by 2 pi radians. Out of the total 2 pi radians, theta angle is taken up. We actually derived this thing earlier, that the area of a sector is 1/2 r squared theta. If you haven't seen that, click this video right here. But anyway, this area here is 1/2 r squared theta, cancelling the 2 pi's of course. The 2 pi and the pi cancel, and then we have 1/2 r squared theta. For this particular circle here, since the radius is equal to 1, what we have here is that the red area plus the green area, or the area of sector OAB, this area, is equal to 1/2 times 1 squared times theta. So I'm going to take that 1 squared out and just write that this is equal to half times theta. Half times 1 squared times theta is half times 1 times theta is half times theta. As for the other area, the red area, the area of the triangle OAB, we're going to draw that separately and try to figure it out. So drawing this thing separately, what we have here is a triangle with a certain base, two sides which are each of length 1, like this. So here I'm going to label them in orientation. This is 1, this is 1, this is something else we don't know, but this side is theta. So here I'm going to drop a perpendicular down like this, such that this is 90 degrees. And here we can see something. This is exactly this triangle OAB. In fact, I'll mark them OAB. This height here, as I labeled earlier, is sine theta. Over here, the triangle's area is going to be half into base into height. Since we have a perpendicular here, this can be considered base, in which case this will be the height. So therefore, the area of this triangle is half into base into height, which is half into 1 into sine theta, which is half sine theta. Substituting that in up here, the triangle OAB has an area of half sine theta. You might see where the sandwich theorem is going to come in here, the squeeze theorem. We can see we have three functions, and two functions are external, one is internal, and we have the less than or equal and less than or equal signs here. If I cut out the half here, we can see that sine theta is less than or equal to theta, which is itself less than or equal to tan theta. We're first going to rearrange this thing a little bit. We're going to divide everything by sine theta and say that 1 is less than or equal to theta divided by sine theta, which is less than or equal to tan theta divided by sine theta. What we actually wanted was sine theta divided by theta. Oh, as up here, sine x divided by x, so we're going to flip the signs as well. Now remember, since all of these are positive, we can do this when we flip the signs. These things also need to be flipped. So here we have 1 divided by 1, which has to then be greater than or equal to sine theta divided by theta, which has to then be greater than or equal to sine theta divided by tan theta. And tan theta I'm actually going to write directly as sine theta divided by cosine theta. If you don't remember this one, go to this video right here. So then simplifying everything out, we can see that 1 is greater than or equal to sine theta divided by theta, which is itself greater than or equal to, here sine theta divided by sine theta is going to be 1, and then 1 divided by cosine theta is going to be cosine theta. So here we have this. Now then, applying the squeeze theorem into this thing, the limit of x going to 0 from the plus direction of sine theta divided by theta is going to be the limit of this thing and this thing. And actually, to do that, we need to first check that both of these are agreeing. On the left side, we have the limit of a constant. The limit as x approaches 0 plus of 1 is 1. And we also need to check cosine theta. The limit as x approaches 0 plus of cosine theta is in fact 1. It is the cosine of 0, which is 1. Here we have that cosine theta is a well-defined function, and around it also its constant range is perfectly defined, and therefore it is smooth, and its value at x equals 0 is 1. So cosine 0 is 1, which means this side also is 1. So that means that our greater limit and our lower limit are both agreeing. These two are both equal to 1, meaning that the thing in the middle from the squeeze theorem that we discussed above is also going to be equal to 1. So therefore, at least from the plus side, sine theta divided by theta is equal to 1. Now, remember, this is not sufficient. We need to check from the minus side as well and confirm that that is also equal to 1. So here I have drawn the diagram that's required for finding the left-hand limit, as in the limit from the negative direction as x approaches 0. Here we have an angle. This angle is in the right side direction, is in the clockwise direction, therefore it's a negative angle. And I've drawn out the red area, the green area and the purple area relevant to this triangle. So here we can see the area of the triangle OCB is greater than the area of the sector OAB, which itself is greater than the area of the triangle OAB. So now, what are these areas? Well, over here, this length right here is tan theta, but it's negative of that. Why is it negative of that? Well, even though the magnitude of tan theta is still the same, remember that its value is inverted. Tan of negative theta is the negative tan of theta. So due to this actual length here, this length here is inverted. This length is not a positive value, it's a negative value. So because we are only interested in the absolute value of the length, because we are not actually interested in the sign or anything, we want the actual positive value, we take negative tan theta. For the same reason, even though this length is sine theta, it's sine theta in negative direction, we want the absolute value of the length, which is actually the length, so we want negative sine theta. Similarly, this angle is negative, but we want the physical actual magnitude of the angle. So what we want is negative the angle theta. So here, this angle theta, if we represent it as a positive quantity, it is negative theta. So then, what are these areas? Well, this length is negative tan theta, this length is 1, these two are perpendicular to each other, so therefore this triangle OCB is 1 times negative tan theta times a half into base into height. So this is equal to half into base is 1, then the height is negative tan theta, so this is tan theta, and then times a minus 1. This area is greater than or equal to the area of the sector. The area of the sector is half r squared theta. Here the angle is negative theta and the radius is 1. So we have half into 1 squared into negative theta. So negative half theta, which itself is greater than or equal to the area of the triangle OAB. The area of the triangle OAB is base into height. The base is 1 here, you can see it's equal to the radius, and the height is negative sine theta. So half into negative sine theta into 1, which is negative half sine theta. So we have this inequality here. Rearranging, first thing we're going to do is divide everything by negative half, which then gives us that sine theta is greater than or equal to theta, which itself is greater than or equal to tan theta. Note here the switch of the sign. Here, because we divided by a negative value, we needed to switch the signs. Here we have negative half, which we then divided everything by negative half, which means we have to switch the signs here. This gets switched and this gets switched. So now we have sine theta greater than or equal to c theta, which itself is greater than or equal to tan theta. Dividing both sides by sine theta, we get that 1 is greater than or equal to theta divided by sine theta, which is greater than or equal to tan theta divided by sine theta. Now inverting both sides, once again when we do 1 over, since each of these values is now going to be a positive value, when we do 1 over, we have to flip the sign again. So here we have 1 is less than or equal to sine theta divided by theta, which itself is less than or equal to sine theta divided by tan theta. So now we have 1 less than or equal to sine theta divided by theta, which is less than or equal to sine theta divided by tan theta. Sine theta divided by tan theta is cosine of theta. So what we have here is that 1 is less than or equal to sine theta divided by theta, which itself is less than or equal to cosine of theta. So here, to apply the squeeze theorem, we need to check the left hand side, this thing, and this thing's limit as theta approaches 0. So what we need to do is check the limit as theta approaches 0 from the negative direction of 1, and the limit as theta approaches 0 from the negative direction of cosine of theta. So the first thing, this right here, 1 is a constant. Because 1 is a constant, taking the limit of the constant is just that constant. So this is equal to 1. As for cosine of theta, the limit of cosine of theta as theta approaches 0 from the negative direction is also the cosine of 0, which is going to be 1. So here the two limits agree with each other. This is equal to 1 and this is equal to 1. Therefore the thing in the middle is also going to be equal to 1. So therefore the limit as theta approaches 0 from the negative direction of sine theta divided by theta is going to be equal to 1. So here we can see up here our right side limit. Oh, actually I've made a mistake here. I've put x here for some reason. It's actually theta. Limit as theta approaches 0 from the positive direction of sine theta divided by theta is equal to 1. That's our right side limit. And similarly, we just proved the left side limit, that the sine theta divided by theta as theta goes to 0 from the negative direction is also equal to 1. So therefore, if the left side limit and the right side limit agree, then the overall limit shall agree. So therefore, finally, actually I'll write it on this page up here. The limit as theta approaches 0 from both directions of sine theta divided by theta is equal to 1, hence proven. So here you can see the general pattern. If you don't know a limit very well, like if you don't know it from previous results, in order to find the limit, you need to do the left side limit, right side limit, make sure the limit exists, make sure both left and right agree, and find the value. So here we've shown, using this geometrical method, that the limit from the positive direction of sine theta divided by theta as theta goes to 0 is equal to 1, and the limit from the negative direction as theta goes to 0 of sine theta divided by theta is also equal to 1. Hence the overall limit as theta goes to 0 of sine theta divided by theta is also equal to 1. Hence proven. So that will be it for this video here today. We've proven some limits and discussed theorems on limits. To summarize, at the very start we learned that one way to find the value of a function is to simply substitute that value into the function and find the value. However, this thing has some problems. Sometimes it doesn't work, sometimes it gives you undefined values or such, in which case the better way to find the value of the function is to take the limit as x approaches that value of f of x. So here these two are essentially the same but different approaches to find the same exact thing. F of a tries to directly substitute the value and calculate numerically the value, and the limit tries instead to take values that are close to the value that you want but not exactly the value you want, and bring those values closer and closer in order to find what the value of f of a is approaching. Not exactly equal to, but rather getting closer to. Here we discuss cases where it works, where we have both sides approaching the same value, right here like this. We considered cases where both sides are approaching different values, then they don't agree. We call them the red limit and the blue limit, or the right-handed limit or the left-sided limit. We discussed their notation as this. The red limit is the limit as x approaches a from the positive direction, known as the right-handed limit. And then what we call the blue limit was the limit as x approaches a from the negative direction, as in when we go from the left versus the right. This is the red limit and this is the blue limit. And then we considered the cases where those two limits are equal, where they are not equal, where both limits are equal and finite. We call them convergent and divergent. So we discussed convergence as a word, and divergence as a word. So convergence means that the left side and the right side agree on a limit value, and that value is a finite value. Divergence is all the other cases, different contingencies and issues. And then we considered some simple rules regarding limits, such as the limit of a constant, limit as x approaches a of a constant being that constant. we discussed that the limit as x approaches a of a constant times a function is equal to the constant times the limit of that function as x approaches a of fx. We discussed that if you have a sum, the limit of the sum is equal to sum of the limit, right? The limit of sum equal to sum of the limits. We discussed similarly how the product of a limit is equal to the limit of the products and vice versa, and we discussed how the one limit divided by another is equal to the limit of the two functions divided by each other, provided that the bottom function is not equal to 0. And then we discussed how the limit of some function to the power of n is equal to the limit of that function, whole thing raised to the power of n. Similarly, how the nth root of a function is equal to the nth root of the limit of that function. And then we discussed that to stay within the real numbers and prevent certain divide by zeros and other errors, we want n to be element of the natural numbers. So what we discussed was that the limit of fx to the power of n is equal to the limit of fx whole thing to the power of n, for n being an element of the natural numbers. And then we discussed the limit of the nth root of fx being equal to the nth root of the limit of fx. For this one, we had extra condition. We had the natural number condition, and we had the extra condition that f of x is greater than or equal to 0 within the valid range for the limit. And then, using all of these theorems and a bunch of other theorems like the polynomial theorem, where if you have a polynomial, then the limit of the polynomial is simply the value that you get when you substitute the polynomial, as in if fx is a polynomial, then the limit as x approaches a of fx is equal to fa. And the squeeze theorem, we use those theorems to find that the limit as x approaches a of x to the power of n minus a to the power of n divided by x minus a was equal to n times a to the power of n minus 1, and the limit as x approaches 0 of sin x divided by x was equal to 1. There are a bunch of other limits we need to prove and a bunch of other theorems we need to discuss, such as how we apply these to graphs in order to find values, but we will be discussing those in a future video. For right now, thank you for watching and goodbye.